Semiconductor memory, a critically important and fundamental building block for everything semiconductor, as everything needs memory. Advantest has long been a market leader in this segment. There are all kinds of memory and storage chips, things like SRAM, DRAM, EEPROMs, flash, hard drives, and solid-state drives, or SSDs. Today, we'll mainly focus on SSDs. Some analysts have the SSD market forecasted to reach $86.5 billion by 2030, and it has been growing at a healthy clip of 15% per year. Partly due to COVID and the new work-from-anywhere global economy, but also from growing demand for gaming, IoT smart connected everything, and the explosion of new use cases for artificial intelligence and machine learning. Hello and welcome to Advantest Talks Semi. I'm your host, Keith Schaub, Vice President of Technology and Strategy at Advantest. To help us understand what's happening and where we are going in the memory market, I'm joined by two of Advantest memory experts, Edmundo De La Puente, R&D Director for the MPT 3000, and Stan Tsze, MPT 3000 Global Marketing Manager. Edmundo and Stan, welcome to Advantest Talks Semi.
Thanks, Keith. Glad to be here.
Great. Thanks for coming on the show. So, Edmundo, if we could, I'd like to do a little Memory 101. Can you briefly describe the difference between memory and storage, and what's the difference and why are they different, and what is an SSD and how is it different than a generic memory chip?
Yeah, of course. Memory such as DRAM or NAND, one key aspect is that it can be accessed directly through their own interfaces. Each type defines the signaling and timing to be able to perform typical operations such as program erase and read. Controllers in this case must be designed specifically to talk to these memory devices and would only work with these device types. For example, a DDR4 DRAM controller on an FPGA or SoC will be designed to interface to those devices only. A storage or SSD, they hide the memory behind a controller, and they use a protocol interface to get data back and forth. The controller inside these storage devices handle the memory interfaces and timing and present a consistent image to the host. So that simplifies these interfaces. It makes them more universal. And all of these protocols are spec-based, and the industry are using those pretty widely nowadays.
I see. So could we loosely characterize that as memory chips are more like what we do at package test and wafer test for SoCs, whereas SSD test is more of a system-level test for memory?
Yeah, that's correct. So from the test point of view, the traditional memory chips are tested just like memory by memory testers, and they're focused on exercising the memory inside these devices, whereas the SSDs, they are devices that are interfacing to a host, a CPU, or some other smart component. And from the test point of view, we're looking for basically exercising the interface. We're not looking to exercise the memory in very detail because that has been done already on other steps on the test process.
Okay, Edmundo, thanks for that level setting. Stan, memory test trends. So what are some of the emerging trends and emerging technologies that are driving memory storage test solutions?
That's a good question, Keith. Well, if you look at SSD really, if you track back over 10 years ago, started with SAS and SATA drive. They are hugely installed today. Over the past 8-10 years, we started seeing PCIe SSD growing into the market, right? And more recently, the last 2-3 years, PCIe has actually taken in growth in a very big way. And actually in around about 2019, end of 2019, PCIe actually overtook SAS and SATA in terms of volume shipment, right? And the key benefits of PCIe was that it's basically speed and storage capacity, right? It's able to handle much faster speed using a very small form factor with better compatibility and as well as latency, right? Those are the things that kind of have, make PCIe grow into a big, huge market today. As we move further along, right now we're starting to see a new memory coming to the market in play, and it's a CXL SSDs. And we're starting to see that the benefits of CXL and how it could become a mainstream driver in the coming years.
So you mentioned CXL. This is something new in the market. Can you give a little more detail on what that is? What does CXL mean?
So CXL stands for Compute Express Link, right? It is a new memory solution to enable us to do more machine learning, AI seamlessly, right? And basically the beauty of CXL is it's able to enable memory pooling. One of the problems that we get into is that a CPU or a graphics chip all have their own, let's say, DRAM and memory, and they are unable to share this memory between themselves. One of the things that the benefit of CXL is it's able to enable that memory sharing and memory pooling. And so it is basically a big change in the infrastructure, and it looks like a very promising memory solution for, like I said, AI and machine learning era.
Great. Thanks, Stan. So speaking of speed, let's shift over to the actual protocol. Edmundo, we mentioned PCI Express 5, and it's twice as fast as PCIe 4. And my understanding is Generation 4 topped out at around 16 gigatransfers per second, whereas Gen 5 delivers twice the speed, up to 32 gigatransfers per second, using 16 lanes. So as Stan mentioned, the speed increase, being able to access memory much faster for a lot of these new megatrends like machine learning and cloud-centric computing. But can you break that down for us? I mean, at a high level, walk us through what is this speed doubling? How are we getting it from Gen 4 to Gen 5? And how do the lanes play into this?
Yeah, basically PCIe has been evolving, and for every generation, the data rate is been doubling. So like you said, Gen 4 currently is running at 16 gigabits per second per lane. And, these are serial interfaces. They run very fast as opposed to parallel interfaces with traditional memory. So when we say a lane is actually a duplex communication method where you have a serial SerDes interface that for writing data to the device or transmitting data to the device, and then you have a separate parallel lines for the receiving side. So it's fully duplex. You can send data at the same time as you're receiving data. So it makes it go basically twice as fast. So when we say 16 gigabits per second, but because it's duplex, that actually doubles the bandwidth. And for example, for a by 4 device, the total bandwidth is 16 gigabytes per second. So it's pretty fast. Now, of course, this can scale on the width. There are by 4 devices, by 8 devices, by 16 devices. And so you can increase the data bandwidth by adding more lanes. Now, when you go to Gen 5, primarily what changes is the data rate. The clock doubles from 16 gigabits per second, or the data rate, to 32 gigabits per second. And when we go to Gen 6, it will double again. However, Gen 6 will be introducing a new method for the physical layer, which is called PAM4. And PAM4 adds a third dimension to how you can control data bandwidth, because in PAM4, we're going to be using a different voltage on the transmission and on the receiving end as well. So you not only have a clock that determines how quickly you send data back and forth, but also for every unit of time, you can send twice as many bits because we're using now different voltage levels to encode additional data. So when we go from Gen 5 to Gen 6, the clock will not double in frequency. What's doubling is the fact that we're using voltage to encode more bits. But the net result is that Gen 6 will have double the bandwidth, the data bandwidth, as Gen 5. So it'll be going to 64 gigabit per second per lane.
Okay, so actually that's really interesting for me because I have I come from the RF world, and I'm assuming that PAM here is pulse amplitude modulation. And like you said, you get more bits because you just have amplitude levels of voltage that you can play with. So curious, why hasn't something like that been used in previous generations? I mean, that's been around forever in RF, and I'm just curious as to why it's only now showing up in Gen 6.
Well, PAM4 has been shown multiple times at different technical consortiums, at least for the last maybe 5-6 years. And it's just the industry shifting is what's prevented. They figure they can squeeze a little bit more performance using the traditional SerDes interfaces. And going to PAM4 adds the challenge of, today, typically you worry about the eye opening, which is a single bit. It's either 1 or a 0, so you just have a single eye. But when you go to PAM4, now you're going to have multiple levels. So your transceivers, they get more complicated. It's more susceptible to noise because now, if you have noise on the system, it could impact the voltage levels enough that maybe they cannot be detected on the right logic levels. But it's gotten to the point where if you double the clock once more, the eyes are going to be so small and the data recovery is going to be very difficult. So it's kind of at the point where, okay, we need something new to be able to scale on the data communications. And PAM4 is actually the beginning, right? There's PAM6 and you can encode more and more bits on the voltage domain. But so right now it's kind of a switch on the industry is starting to adapt that because of the difficulties of maintaining the single bit and just doubling the clock.
I see. So really the industry has kind of reached a roadblock and they are forced to implement this new dimension to get the data rates higher. Okay. Then just to follow on to that, with PAM4, right, you've got 4 voltage levels. What sort of voltage range are we looking at? And like you said, wouldn't that be a challenge because the voltage from level 0 to level 1 is now pretty small compared to what it was in previous generations? Is that a problem?
Yeah, that's the challenge right now, which is when in the past, the eye height had more margin, right? As long as you were within the eye mask, it was easier to achieve. But now the eye masks are going to be, the voltage is going to need to be more accurate and so that you can detect the different levels. But I believe it's the same amplitude, it's just being subdivided into more levels to be able to send 2 bits as opposed to 1 bit.
Thanks, Edmundo. Then the next question, what sort of AI applications are driving this need for speed, and why is it so important, and how does the speed doubling help? And are there other innovations like lane scaling that could impact the memory chip manufacturing or the memory test solution itself?
The memory bandwidth requirements has continued to grow over time, primarily because of the amount of data that is being consumed by devices or applications. One example would be autonomous driving vehicles, which they use lots of data to manage the systems. There's also been some trends on power. If the only way to get higher data bandwidth is to double the width, let's say you go from 4 lanes to 8 lanes and you get twice the bandwidth, that actually consumes more power than if you go faster and you stay on the same number of lanes. Or somebody could say, hey, I don't need additional bandwidth, but I want to save power. they could go from, say, a by 8 down to by 4 at a higher data rate, and that actually will save some power. So it's really data consumption applications that are just pulling a lot of data and some power management, because these devices, as they go from generation to generation, power keeps going up. And that's another concern.
Do any of the generations 5 or 6 support something like lane scaling? So say you laid it out for 8 lanes, but in most cases you could get away with 1 or 2 lanes and save that power for the appropriate speed, and then you could scale if necessary, but dynamically.
Yeah, so basically there's this feature called lane masking where you can scale down. Let's say you have, like you said, 8-bit interface or 8 lanes, but you just want to use 4. So then you could do that. That's no problem. They could also use some of the lower power modes. There's another whole dimension on CPUs, at least, and other devices where, depending what you're doing on the application, you could slow it down to save battery or power. So there's some power management tools, as well as, you can reduce the number of lanes. You give up some of the bandwidth. But, if you had a system that was using Gen 4 by, let's say, Gen 4 by 8, and you want to cut back some power, you could go to Gen 5 by 4. Well, now that we're going to have Gen 6, you could even go to Gen 6 by 2. You get the same bandwidth, but you don't have to interconnect 8 lanes, because routing these lanes on a PCB is not trivial because the speed is so high. There needs to be a lot of care, making sure that signal integrity is designed properly. So connecting 2 lanes is a lot easier than connecting 8 lanes, even though they're going faster, but still the problem can be managed better than having too many lanes.
Great. Thanks, Edmundo. So, Stan, before we move on, any comments that you want to add?
Maybe one thing to note here is, just so that we kind of understand the capacity of what Edmundo is talking about, right? So today we're all talking about zettabytes, right? We have come a long way from megabyte, and now we're talking about zettabyte. As we actually talk about Gen 5 and beyond, Gen 6 and beyond, and CXL, the world is going to come to a term called yottabyte. 1 yottabyte is 1 million trillion megabyte. And to think of that kind of scale in a data center, running AI application and machine learning, that's what the world is heading into. And that's going to, pose a lot of challenges.
Actually, Stan, that's perfect segue into sort of the next question, where we're talking more about the recent explosion of AI and machine learning, and how these new applications require high performance computing, but also the tremendous amount of memory. And you just mentioned yottabyte type size of memory is coming. So what sort of impact is this having on cloud-centric examples? What I mean by that is cloud-based applications have higher latencies than edge-based applications. But a lot of the enterprise workloads are still moving into the cloud. And how do we deal with cloud network latencies being slower than edge-based? Edmundo?
Well, yes. Basically, there's now these memory compute architectures where, traditional memory structures, there's a bus between the CPU and the memory, and data, whenever the CPU needs data, has to get it across this bus. But when you need to get lots of data very, very quickly, you want something that has very low latency. And the buses, especially protocol buses, they add overhead. So it's difficult to get data fast. So now the question is, okay, how do we integrate memory much closer to the CPU so that some of these computations can be run at a much faster pace than getting data from a server or even within the same system, right? If you had DRAM on the motherboard to a CPU, there's going to be some amount of latency before the CPU can get to the data. So the push now is to move memory closer to the CPU so that these and big amounts, so large amounts of data. But yeah, definitely the server, the cloud is great for data storage where you don't require very, very low latency, but you need this large amount of data that needs to be transferred back and forth. But some of these new applications, that's not going to work.
All of this is driving fascinating new memory architectures, and you alluded to this, I guess, in-memory compute type architecture. I'm pretty sure this is creating a lot of new key test challenges, and companies like Advantest with the MPT 3000 have to address those challenges. So how are we doing that, and how does the MPT 3000 address those types of challenges?
The challenge is, is basically twofold. The first one is for us, an MPT, we've done a pretty good job to meet the time requirements. We are typically challenged where we're looking at designing a system to test future devices that are not in the market yet, of course, and customers need a solution to get the tester qualified and the device qualified, all of those things. And this is nothing uncommon with ATE. We're always designing systems with sometimes technology that is not quite ready. And so it becomes an interesting challenge from that point of view. But also, cost of test, of course, every time this frequency doubles, we have to use more expensive components. Even when you talk about PCB materials, it doesn't get any cheaper, but there's always the challenge that we have to maintain certain cost of test. We cannot just double the cost of the system. And so that drives us into very creative solutions, how to minimize the impact of just going faster. And then, of course, power is always it's always there as a challenge. The devices now consume a lot more power, and we want to make sure that our throughput doesn't suffer, where we want to maintain our parallelism so customers can test many devices at the same time. But as these generations of technology, PCIe, they get faster and faster, it's a challenge, and we've been able to sort of solve a lot of these issues and provide a solution that does not, double the power or cost any of that.
I see. Stan?
Yeah, sure. On top of that, we're always seeing a lot of change in, the SSD form factor, right? From M.2, for client base. And then there's U.2, U.3, E1.S, E2.S, you can name it, right? There are many, many form factors. So that is the other thing challenges that we are also having to deal with. And finally, workload, right? We're always constantly thinking about how do we have an architecture that can deal with all these workloads, multiple, different protocols, and testing at a high volume, right? And that's always a challenge.
Great. Thanks, Stan. What drives having so many form factors?
First of all, different segmentation, right? So if you look at client and mobile, right, they are always getting smaller and smaller, right? So M.2, it's a very big form factor. Now that cars are coming up and things like BGA is going to start coming up, right? So that different application, on mobility and things like that drive, it's one driver. So basically the segment drive different form factor, right? And people are always, as what Edmundo was saying, right? The power keeps getting more and more on, because you are handling more and more data. And so one way to handle it better, a lot of SSD vendors are trying to differentiate by introducing new form factor, right? Look at Intel, this ruler, this is their way of they are trying to drive that as a standard, right? And if driving a standard in a form factor and a lot of people adopt it, it actually helps them, it's about market share as well, right? So basically different different segmentation and different application will continue to drive all this form factor on and on. I don't think it will stop. It will keep going on and going. And every generation you see someone is trying to come up with a different form factor And as a way to kind of edge the competition, right? I think Intel is trying to take over the data center world by coming with this long ruler. They haven't been very successful yet, but I think that's what they're trying to drive at, right?
That brings us to the end of the show. I'd like to thank each of you, Stan, Edmundo, for coming on today and helping us understand all the exciting innovations happening in the flash memory market. And best of luck with the Flash Memory Summit.
Thanks, Keith. That was fun.